All right, so the first thing that we're going to talk about today are the concepts of self and mutual inductance. So I'm going to bore you guys with a little bit of electromagnetic field theory here. So how many of you guys have had a class in which you've dealt with Ampere's circuit of law or Ampere's law? Ampere's law. You should have. So then you should have seen Ampere's law before. All right. So according to Ampere's law, if we have a wire, which I'm just going to designate as this black line right here, I'm putting these ellipses to just say that this section of wire continues in both directions such that we're forming a closed circuit at some point in this thing, right? So I've just got a section of wire. And then I have a current flowing down the wire that I'm going to call I of t here. The current doesn't have to be time varying, but I'm choosing to list it as a time varying current. So Ampere's circuit of law tells us that whenever we have a current flowing down a conductive path, we are going to generate a magnetic field. Does that sound roughly familiar, right? Are you guys familiar with the right-hand rule for determining the direction of magnetic fields when you have a current? So if your thumb points in the direction of, if the thumb on your right hand points in the direction of current flow, your fingers curl around in the direction of the magnetic field. So the way that I have the current flowing down this wire, we should see that at points in space above the wire, the magnetic field is exiting the screen towards you guys. And at points in space below the wire, it is flowing into the screen. So I'm going to represent that as follows. Right. So coming out of the board, I'm going to put as a dot inside of a circle. And so what I'm trying to represent here is if we are effectively like staring down the face of an arrow coming at us, all we could see is the tip of that arrow. And then into the board is going to be a circle with an X in it. And so that's us effectively seeing the back of the arrow or the fletching or whatever as we're looking at it traveling away from us, okay? So these field lines that I've tried to write here in this light blue color are the magnetic flux density lines B, and they will vary as a function of time as well as a function of space. So the further away we are from the wire, the different the intensity of the magnetic flux density will be. Okay? Where our magnetic flux density B is measured in the units of Teslas, where a Tesla is nothing more than a Weber per meter squared. And since most of you are probably not familiar with the unit of a Weber either, we'll expand it one more time and say that 1 Tesla is equal to a volt second per meter squared. So let's say that instead of having a long straight section of wire, we wrap the wire up to form a coil. So we might have something like this, right? So I'm going to put this cylindrical shape here. That's what we're going to call our core. And when we get into 360, we're going to spend a whole heck of a lot of time talking about the materials of the core and its properties and how it affects things. But for now, we're not going to worry about that too much. So I've got my core, and now I'm going to wrap a wire around it. And the direction that I wrap my wire around things is actually very important because that's what's going to tell me the direction of my magnetic flux density vector in that space. So right now I'm going to wrap the wire around this core so that it goes along the outside, then around the back and over and over and over again. Like so. And I'm going to define my current such that it is traveling down the wire in this direction and coming out of the wire in this direction. Okay. The coil that I have formed here will have some number of turns, n. So that's what we're going to use to represent as our variable for the number of turns. So just as a quick conceptual thing, who among you can tell me what electrical component I've effectively just described? Coil of wire. So that is a solenoidal inductor. Absolutely right, right? So solenoidal inductor. So with our wire wrapped around the outside of that core, we can also use the right-hand rule to tell us what direction our magnetic flux density is going to be. So as it works out, if our fingers wrap around in the direction that the wire is wound, our thumb gives us the net direction of our magnetic flux density. So the way that I've drawn this particular solenoidal coil, we should see our magnetic flux density field lines oriented in a vertical direction. So directly along the axis of symmetry, I did not mean to erase that. We should see something like this. And as we get away from the axis of symmetry inside of our solenoidal coil, we'll see that our field lines will start to wrap around to form a closed path. So something akin to this. So I'm just going to put a line here that's in parallel. Like so, where this is the direction of my field as it wraps back around. Put another one this, and we can put some on the other side of our coil as well. Like so. Where once again, all of these light blue lines are representing our magnetic flux density B as a function of time. So the reason why we might wrap our wire up into a coil is so that we get to concentrate our magnetic field lines and create a larger magnetic flux that's passing through our core material, okay? So our magnetic flux, I'm going to call this phi B. And it is measured in Webers, where a Weber is nothing more than 1 volt second. So our magnetic flux phi B mathematically is just the product. Actually, because I have a time varying field, let's say that phi B of t is equal to B of t times A, where A is the cross-sectional area of the medium that our magnetic flux density vector is passing through. So the cross-sectional area of our solenoidal coil is just the area of the circle that our coil is wrapped around, right? So this area that I'm going to color in gray right here would be our cross-sectional area A. So inside the coil, we have a very large magnetic flux density because we have all of those field lines passing through a very small amount of space. And outside of the coil, we have a very, very low magnetic flux density because we're allowing those field lines to pass through effectively all of the air outside of the coil, okay? So wrapping our wire around a core like this gives us a region where we have a very, very strong magnetic flux density vector, right? That's the reason we use solenoidal coils, toroidal coils, all of that kind of good stuff. So now I'm going to define another quantity here. This is what's known as the flux linkage of the coil. So flux linkage will be the letter lambda. And it is also measured in Webers. So what the flux linkage represents is the total amount of flux that's passing through something. So mathematically, our flux linkage here, it'll be time dependent, is just n, the number of turns, multiplied by our magnetic flux. So we've defined flux, magnetic flux in terms of the B field, and now we've determined flux linkage in terms of flux, okay? So in a linear system, flux linkage and current are related to each other by the self-inductance of the coil. And so that mathematical relationship is flux linkage as a function of time is simply L, our self-inductance, times our time varying current. According to Faraday's law of electromagnetic induction, a voltage will be induced across our coil if the magnetic flux linkage changes. So our induced voltage, V of t, and I'm going to represent that on our picture here as the positive polarity terminal of our voltage is the terminal that the current is flowing into, and the negative polarity terminal is the terminal that the current is flowing out of, is simply the derivative of the flux linkage with respect to time. If we substitute in our relationship for flux linkage in terms of self-inductance, we have the derivative of L I of t. And so this just comes out to be L times the derivative of the current with respect to time. And this is the exact relationship that we talked about earlier on in this class when we were developing our phasor domain relationships for everything, right? So in the time domain, the voltage drop across an inductor is simply L times the derivative of the current flowing through the inductor. This is now the second time you've seen it, and this is an explanation effectively of why that relationship exists. So self-inductance is a quantity because the magnetic flux that's generated by this coil winds up causing a magnetic field that flows through the coil itself. So that's why we have self-inductance. If we were to move a second coil close to this first coil, we might have what's called mutual inductance. So I'm going to try to kind of graphically describe what's going on here. Okay. L is the self-inductance. So let me put that here. Self-inductance measured in henries, where a henry is a volt second per ampere. So this is literally just the inductance you're used to dealing with. Nothing remotely different.
Is it easier to derive self-inductance first, or
Definitely self-inductance first. All right, so we're going to consider a new scenario where now we have two coils, okay? So let's just say that we have a simple circuit and we are sinusoidally exciting it. Doesn't matter if we're exciting it with a voltage source or a current source. We can sort all that kind of stuff out later. And here, I'm just going to represent my coil as a coil of wire, something like this. And let's say that my current, I'm going to call this I1 of t, is flowing in this direction. And my induced voltage across this coil one will be V1 of t, and I'm just going to make a note here that says coil 1 has N1 turns. Because it's a time varying current. So capital letter is typically used for DC because we are dealing with time varying quantities. I'm going to put it as a lowercase. Yep. That is the convention that I usually use. Now, just as a side note thing here, typically speaking, when we represent things with phasors, the reason why I use capital letters for those, even though they are representative of time varying quantities, the quantities for the phasor itself, the magnitude and the phase angle do not change. So they are effectively constants. And so that's why I use capital letters for those. And we also get to use DC circuit analysis when we are in the frequency domain or the RMS phasor domain. Another reason why I typically use capital letters for those quantities. Yep. All right. So we've got one section of this overall system put here. Now I'm going to introduce on the right-hand side of the system another coil. Yep. This is telling me that this coil has a specific number of turns. So now we have a second coil over here. I am leaving this coil open circuited, so we're not going to see any current per se. This coil will have, so coil number 2 has N2 total number of turns. And now let's look effectively at what's going on with our flux. Okay. So coil number 1, no. So coil number 1 is carrying some amount of current. So we should see that we are having some amount of magnetic flux that's going to be flowing around in our circuit. So I'm going to call this flux phi 11. So this is the flux generated by coil 1 that's passing through coil 1. Okay. And just for the sake of argument, I'm going to say that it's going in this direction, right? So here we have some flux phi 1, and I just want to be really clear. All the subscript means, so the first subscript is the coil that's generating the flux. The second subscript is the coil the flux is passing through. Okay, so phi 1 means coil 1 generates a flux that passes through coil 1. Well, over on the other side, we're going to have a flux, and it might pass through coil 2, like so. And so I'm going to call this flux phi 1, 2. Okay. Since there is a magnetic flux that is passing through coil 2, and I1 is a current that is time dependent, what we should see is that we will induce a voltage across the terminals of coil number 2. Right? So I'm going to call that voltage here V2. So we can mathematically describe this induced voltage by just using the definitions that we've already developed, right? So the voltage V2 would be the derivative of the flux linkage of coil 2 with respect to time, which should be the derivative of the number of turns in coil 2 times the flux passing through coil 2 and keeping on expanding things here, we're going to have N2. Now we're going to describe our flux as it's related to the number of turns, the current, and the self-inductance of coil 1. So this is going to look like L1 over N1 times I1 of T. And now I'm going to pull out constant terms effectively, right? So I'm going to have an N2 over N1. So that's what we're going to call our turns ratio when we deal with transformers next week, times the self-inductance of coil 1 times the derivative of the current I1 with respect to time. And we are going to call this expression right here, N2 over N1 times L1, our mutual inductance M21. Mutual inductance is also measured in henries because it's just a ratio of turns, which is a dimensionless quantity, times a self-inductance. N2 divided by N1 times L1. Yeah. So what this mutual inductance represents is effectively the strength that these two sides of this circuit are coupled together, right? So if we had two coils that were very, very far away, we should see that the mutual inductance between them is very, very small. When they're very, very close together or wrapped around the same core, which is how we form a transformer, it's going to be quite large. So if we were to reverse the roles of the coils here, so let's say that we had excited coil 2 and left coil 1 open circuited. So let me write that down. the induced voltage on coil 1 would be V1 of T is equal to the derivative of the flux passing through coil 1, excuse me, the flux linkage of coil 1 as a function of time. And after several steps, we would wind up getting N1 over N2 times L2 times the derivative of I2 with respect to time, where we would call this quantity M12, mutual inductance seen between our coils. Okay. Now, for energy to be conserved in this system, the mutual inductance M12 must be equal to M21. And so now we're just going to call our mutual inductance M. So it really doesn't matter which coil we energize and which one we leave open circuited. The mutual inductance seen between the two coils is going to be constant. Okay. All right. So let's see what happens if we were to effectively close the current carrying path of our second coil. Okay. So if both coils are excited, so something like this, so we're sinusoidally exciting coil number 1. So here is our voltage V1 of T. Here is coil 2. And we sinusoidally excite this one. Realistically, we don't even actually have to sinusoidally excite it. We just need to close this path so that current can flow, but we'll get to that in a moment. Here is our voltage V2. Let's say that I1 is flowing in this direction. I2 is flowing in this direction. What we should see is that arbitrarily, we're going to have some flux phi11 circulating around this way. We're going to have some flux phi22 circulating around this way. And then we're also going to have a flux that's going to link these two together. And for the sake of argument right now, I'm just going to call that phi. So we could call it phi12, phi21. It's the exact same thing either way. It's just the flux that's linking those two coils.
I'm assuming you would just have four types of flow, like you have four flux relationships, right? So the two in the middle, are they just combining the one?
Effectively, yes. And so how they combine is dependent on the direction that the coils are wound. So if the coils are wound in one particular way, the fluxes will add together. And so let's say that we had so if we look at the direction of how things are flowing in this guy right here, right? So we can say, and I'm kind of playing fast and loose with the drawings because it's hard to detail the direction of a winding, which is why we use the dot convention, which is the next thing that I'm going to introduce. So this first coil is generating a flux that's flowing in this direction around here, and it's going to be going in this direction. This coil over here is generating a flux in this way, and so when its flux is passing in this direction, we're going to see that those two fluxes effectively oppose each other, right? So that mutual flux between them is actually going to wind up taking away from the overall flux in the system, and so we would describe that where we're going to see we should have a negative value for our mutual inductance because it's taking away from the overall inductance of the system. If we wound our coils in such a way that instead of the fluxes opposing each other, they would combine and add, we would wind up getting a positive mutual induction term.
I guess what I'm confused about is the bottom, like, everything below the halfway point, from a physics perspective, I can't imagine how they, and I know that you're not drawing to be like literal in like every physical thing.
Right.
That's something, because I know there's great.
Yep, has to be. There is no such thing as a magnetic monopole. There's only magnetic dipoles, which means our field lines have to curl back in on ourselves, which means our flux has to curl back in on ourselves and form a closed loop, 100%.
I guess I'm confused how the bottom would ever form cohesive circles. Like you have two rings, the tops will be the, but the bottoms are always. Yeah.
But they're not all, so think about the top part of the coil is effectively driving flux out of the top. And we know that that flux has to circle back around to come into the bottom polarity terminal.
The bottom, at some point, they're pushing out of the bottom is pushing in.
Yeah.
Creating.
So yeah, so the top is pushed as forcing flux out. The bottom has to be kind of sucking flux in a sense. Okay, so we have this system where we have excitation on both sides of our network, just containing our coils here, right? So the flux linkage for coil 1 is going to be the self-inductance of coil 1 times the current that's passing around coil 1 plus the mutual inductance between the two coils times the current I2. So that's what our total flux linkage is going to be. So the total flux here should depend on not only the self-inductance, because we know that coil 1 generates some amount of flux that flows back into coil 1, but also a mutual inductance term, because coil 2 is generating some amount of flux that's passing through coil 1 as well. Very similarly, we'll have a flux linkage lambda 2 that will be L2 I2 plus M I1, so that the total voltage is going to wind up having not only a self induction term, but also a mutual induction term, right? So the total voltage across coil 1, V1, is nothing more than the derivative of that flux linkage. And so that's going to look like L1 times di1 by dt plus, for now, m times di2 by dt, and V2 will be the derivative of flux linkage 2, which is just going to be L2 times the derivative of I2 plus M times the derivative of I1 with respect to time. All right, so total voltage is some combination of a self-induced term and a mutually induced term. We're going to sort out the signs for all of this kind of stuff here in a moment by using what's called the dot convention, okay? So the dot convention is effectively a requirement, at least from a function of schematic diagrams, because it is not easy to convey the direction that a coil is wound on a circuit schematic. So we use a dot convention to effectively take care of that for us. Before we do that though, right now we have everything here in the time domain. We are not going to analyze any of these circuits in the time domain whatsoever because that math is entirely too gross. Instead, we're going to analyze all of our circuits in the frequency domain. So I want to take a quick pause here and try to sort out what this is going to look like as a frequency domain calculation. So in terms of impedances, phasor voltages, phasor currents, all of that kind of good stuff, right? So here's our time domain representation. So down here, let's do our phasor domain representation for this exact same thing. So, sorry, this should not be as a function of time because we throw away our time dependency. So I'm going to have L1 times the derivative of I1 with respect to time. Okay. So I want you guys to think back to when we were describing our phasor domain relationships for an inductor in particular, right? So we were doing this exact operation when we were looking at our phasor domain relationships. And what we learned effectively was that taking the derivative in the time domain is nothing more than multiplying by j omega in the frequency domain. So instead of having L1 times the time derivative of the current, this is literally just going to look like j omega L1 times our phasor current I1. And very similarly, taking the time derivative of I2 is just going to be j omega times our mutual inductance times our phasor current I2. So if I give you anything in the time domain, all I'm expecting you to do is just multiply by j omega and get rid of that damn derivative. Okay. I believe it would be a waste of time for you guys to do it in class. If you want to see the math in the time domain, I can definitely give you a link to one of my videos from ENGR 221. So that's just the normal circuits one. Effectively, I work a very simple problem fully in the time domain with the entire point of that as to scaring everyone away from ever doing that math in the time domain again because of how much of a pain in the ass it is. It is 70% trig identities, 30% actual useful math. Yeah, so that's why we just don't do it, because it's just gross trig identities over and over and over again to make it look like how we want it. Whereas if we just work it using complex numbers, we get the exact same result in seconds as opposed to minutes. Yeah, if you want to see me struggle through trig and algebra for 45 minutes, I'll definitely show you the video, but I'm not going to waste our time in here with that. Yeah, and it's just a resistor and an inductor.
Oh, well,
Mm-hmm.
Did that change in frequency? Like, does that equation alter the phasor?
So yes, the value of the mutual inductance or let me put it this way. The impedance of the mutual inductance is definitely going to change as a function of frequency. 100%. Because it's just a combination of inductance, and inductance changes as a function of frequency. So our phasor induced voltage V2 is just going to be J omega L2 I2 plus J omega M times I1. All right, so just wanted to tie this back to the frequency domain analysis that we're going to be dealing with. By the way, if we were wanted to work in RMS phasor domain instead of the regular frequency domain, just put a tilde on top of all of the phasors and it's the same exact relationship. Nothing, no change. All right, so now let's talk about the dot convention. So a dot convention is nothing more than a way for us to characterize how the windings of our coils work with respect to each other, okay? So instead of trying to articulate how the coil is wound on a schematic diagram, instead, we literally just put a dot. So our circuit where we had excitation on both sides of our system might be represented by something like this. I'm giving myself plenty of room here. So now that coil is just represented by some self-inductance L1, and I'm going to put a dot like so. And what that dot does is it effectively indicates the positive polarity terminal for this coil. It doesn't actually really mean anything other than, hey, this coil is wound in this particular direction. So our current I1 of T is flowing into the dotted terminal in this case. Here is our voltage V1 of T. And then over on the opposite side, I would have an inductor representing my self-inductance L2. I'm going to put the dot on top like so because current I2 is flowing into the dotted terminal. Give myself some room here, put my excitation source over here. And here's my voltage V2. And this voltage V1 is still L1 di1 by dt plus M di2 by dt. And this voltage V2 would be L2 di2 by dt plus M di1 by dt in the time domain. Actually, one other thing that I'm going to introduce here. So this double-sided arrow here effectively just represents, or this is our way of saying, hey, there is a mutual inductance between these two coils. Okay. So we're saying coil 1 represented by inductance L1 and coil 2 represented by inductance L2 are magnetically coupled to each other, and they have a common mutual inductance of M. Okay. So now let's talk about the rules for which we assign the signs or the polarities of these voltages. And this is where it's going to be confusing until it clicks effectively, okay? So what I'm about to give you is effectively a roadmap that if you are like, I'm not sure about what sign this thing should have, look at this and it'll tell you exactly what's going on, okay? So we'll start by saying the self-induced component of our voltage V1 of t is assigned a plus sign if A, the positive polarity of the voltage V1 is at the dotted terminal, and so both of these situations have to happen concurrently. I1 of t enters coil 1 at the dotted terminal. So let's look at the situation that we have right now, okay? So here is the positive polarity of our voltage V1, right? It is on the dotted side. So the positive polarity of V1 is at the dotted terminal. That part is true. And the current I1 is entering the coil at the dotted terminal. So the current I1 is flowing around the loop in this direction, so it does enter the dotted terminal, which is why that L1 times di1 by dt has a positive sign. Okay. The other case that we would put a positive sign on the self-induced component is if the positive polarity terminal of V1 of t is at the undotted terminal, and I1 flows into the undotted terminal. So I want to be clear here, this is a semantic thing, but voltage doesn't flow. Voltage appears across terminals. So if we put the positive polarity of the terminal at the dotted terminal and the current flows into the dotted terminal, we give it a plus sign. If we put the positive polarity terminal at the undotted terminal and the current flows into the undotted terminal, we also give it a plus sign. So if it is mixed, so if the positive polarity terminal of the voltage is at the dotted terminal, but the current is flowing into the undotted terminal, we're going to give it a minus sign. So now let's talk about the rules for the mutual term, and it's effectively the same thing, except that now we're going to be looking for whether the whether the positive polarity terminal of the voltage V1 is at the dot and what terminal the coil 2, or excuse me, the current I2 is flowing into. I'll make some sense of it here in just a second. I just expressed that very poorly. All right, so bless you. The mutually induced component of V1 is assigned a plus sign if criterion A, the positive polarity of V1 is at the dotted terminal and I2 enters coil 2 at the dotted terminal. So before we do the undotted on both sides things here, let's look at stuff really quick, right? So just to be clear here, the positive polarity terminal of voltage V1 is at the dotted terminal for coil 1, right? So that's our first criterion to give a plus sign. Our current I2 is flowing into the dotted polarity terminal of coil 2. So that's why our mutual term has a plus sign right here. Okay. So we're looking for the voltage bit on coil 1 and the current bit on coil 2 when we're dealing with the mutual induction term. Okay. So the voltage is effectively always with respect to the coil that we're interested in. And then the current is that same coil if we're doing the self-induced part and a different coil if we're doing the mutually induced part. Okay. We'll put this into practice over and over and over again until we get it sorted out. So, fantastic question. So, what Carrie, right? Casey, shit, sorry. So what Casey just asked was what would happen if we flipped the polarity of the voltage V2? That would change literally nothing for the voltage V1, but it would change numerous things for the voltage V2, right? So when we're looking at what's going on for the voltage V2, it's effectively the exact same rule. So let's look at things really quickly here, okay? So the positive polarity terminal of voltage V2 is associated with the undotted terminal of coil 2 or inductor L2, right? So we can see right here, this voltage is on the undotted side. The current I2 is flowing into the dotted polarity terminal. So that means that the self-induced part should have a minus sign now. If we look at the mutual thing, so the positive polarity terminal of V2 is at the undotted terminal. The current I1 is flowing into the dot. So we should have a minus sign here as well. So if we want positive signs, we want the positive polarity of the voltage to be at the dotted terminal, and we want the current flowing into a dot. Or we want the positive polarity to be at an undotted terminal and the current to be flowing into the undotted terminal as well. Anytime it's mixed up, you get a negative sign. What do you mean by working together? Effectively, if the passive sign convention, which I'm not even sure you guys fully know about, is obeyed, it gets a positive sign, and if it isn't, it gets a negative sign. But that might be another bag of cats that I don't particularly want to open because that's what these rules are for. Do what? Criterion B. positive polarity of V1 is at the undotted terminal. And I2 enters coil 2 at the undotted terminal. And then all other combinations give a minus sign. So let's put this into practice by looking at your in-class assignment. Okay. So we have the following circuit for problem 1. Where we have a voltage of 10 angle 0 degrees volts. Here's a 4 ohm resistor. J3 ohm coil. Dot on the right hand side. J4 ohm coil. Dot on top. And these two coils have a mutual inductance of J1 ohms. Over here, we have a third coil with an impedance of J6 ohms, dot on top, and our J3 ohm coil and our J6 ohm coil have a mutual inductance of J2 ohms. Here's our 2 ohm resistor. Here's a minus J2 ohms capacitance. Here's a phasor voltage VZ that we're looking for. And then while I'm at it, I'm going to define a phasor current IX, like so, and a phasor current IY, like so. And our ultimate goal in this problem is to solve for the phasor current IX, the phasor current IY, and the phasor voltage VZ. Okay. So until we get used to these things, we're going to do this extraordinarily meticulous. Okay. So this is our process for effectively every one of these circuits. It's just going to be mesh analysis, but we're paying special attention to things. Okay. So we're going to apply mesh analysis here. I'm going to introduce 2 mesh currents. I'm going to choose my mesh currents to be in the same direction as IX and IY. I don't really have to do that. I'm just doing it to make things easier in the long run, okay? So I'm going to call this mesh current right here I1, and this mesh current right here I2. I'm going to let you guys decide on the polarity of the voltage drops across each of our coils effectively. So let's start with the J3 ohm coil, okay? Do we want to put the positive polarity terminal on the dotted terminal or the undotted? Ultimately, it will not matter. We're just going to apply those rules to sort out what the signs are. So just make an arbitrary decision. Do you want the plus sign on the left or the right? On the dotted, sure, okay. So I'm going to call this voltage V1. So I'm treating that J3 ohm coil as coil number 1, and Casey has said that the positive polarity terminal should be on the dotted term. Okay, I got no beef with that whatsoever. Brock, tell me whether you want the positive polarity terminal on the dotted or the undotted terminal for the J4 ohm coil. Sure, why the hell not? Nope, none whatsoever. Raymond, tell me whether you want the positive polarity terminal on the dotted or the undotted terminal for the J6 ohm coil. On the dotted, okay. All right, so these voltage polarities were made up entirely by you guys, and in the grand scheme of things, they will not matter at all as long as we apply the mesh analysis correctly. So the first thing that we are going to do is we are going to write an expression for all three of these voltages based on what our mesh currents are doing and all of that kind of stuff. All right, so we're going to start with voltage V1. So the positive polarity terminal of the voltage V1 is at the dotted terminal. Can we all agree on that? The current I1 is flowing into the undotted terminal. Can we agree with that? So that means that our self-inductance term should be negative. Okay. So we are literally just going to have negative J3 ohms times I1. Now, let's sort out what's going on with the mutual inductance term for the J1 ohm mutual inductance, right? So I'm arbitrarily going to just put J1 ohms here and a current of I1 is flowing through coil 2. So that's why I'm putting it here. Okay. So our positive polarity terminal for our voltage V1 is at the dot of coil 1. And the current I1 is flowing into the dot for for coil 2. So just to be clear here, for our mutual inductance term, we're looking at what's going on at this coil right here, right? So the positive polarity terminal of voltage V1 is at the dotted terminal for coil 1. We all agree with that. The current I1 is flowing into the dotted polarity terminal of coil 2. So that means this mutual term is positive. Coil 1 is also magnetically coupled to coil 3. So we are going to have a second mutual inductance term here that we need to pay attention to, right? So I'm going to have that mutual inductance of J2 ohms. A current of I2 is flowing through coil 3. So I'm going to put I2 here. And now we need to figure out what the sign is, okay? So just to rehash things, the positive polarity terminal of the voltage V1, so that's the voltage that we're trying to find, is at the dotted terminal of coil number 1. Has been every single time. The current I2 is flowing into the undotted terminal of the 3, right? Or the undotted terminal of coil 3. So that means this should be negative.
Oh, here, look up there. That's undotted. Because you have your.
So let's explain this stuff. This is why this is tricky, okay? So let's go back through. And let's do this whole thing over, just step by step, okay? So when we're looking at our self term, we're looking at coil one for both the voltage and the current. Okay. So here is my positive polarity terminal of voltage V1. It is on the same side as the dotted terminal. That is true every single time, okay? Now we're going to look at what our current I1 is doing with respect to coil one, because that's going to tell us what our self-induced term is, okay? So our mesh current I1 flows around this left-hand path in a clockwise direction. So our current is flowing into the undotted terminal. So that means we are going to have negative J3 ohms, which is the self-inductance effectively, or the impedance of the self-inductance, times that current I1. Now we're going to work on the mutual inductance term for coil 2. Okay. So we have already established that the positive polarity terminal of the voltage V1 is at the dotted terminal of coil 1. Our current I1, let me do it in this light pink. When it's going around its path, it flows into the dotted terminal of coil 2. So since the positive polarity is at the dotted coil for coil 1 and the current is flowing into the dot for coil 2, our mutual inductance term should be positive. So we will have resistant here plus J1 ohms, which is our mutual inductance seen between coils 1 and coil 2, times the current I1, which is the current that's flowing into coil 2. Now let's figure out our mutual inductance term for coil 3, or the J6 ohm coil. Okay. So our mesh current I2 is flowing up as it goes around its clockwise path when it sees that third coil, right? So once again, the positive polarity terminal of coil 1, or excuse me, of the voltage V1 is at the dotted terminal for coil 1. The current I2 is flowing into the undotted terminal of coil 3, which means we should have a negative sign for our mutual inductance term for coil 3. So minus. Now we put in our mutual inductance impedance, which is J2 ohms, and the current that's flowing through coil 3 is I2. So that is our expression for V1. Raising your hand or giving me a thumbs up?
I do have a
Sure.
quick question. So the basis of this analysis method is your I1 and I2 and plus or minus on the voltages are completely arbitrary. It just has to be consistent throughout your analysis.
Yeah.
Okay.
Like any other analysis.
So we were wondering kind of why that was turned around. It's completely arbitrary.
It is. It 100% is. So I could just as easily have said that I2 is in the same direction as IY, and that would flip that sign on that mutual term, but it'll also flip other signs elsewhere. So, yep. So the directions that we choose for our mesh currents and the polarities that we choose for the voltage drops across our coils are completely and utterly arbitrary. As long as we apply the signs correctly based on the rules, it's all going to work out in the wash, which is why this stuff is a nightmare to grade. Yeah, because everybody can do things differently. 100% right. So on some things, particularly on your exams, I will explicitly give you polarities and directions for currents so that it's not such a pain in the ass. 100% right. All right, so we've spent 15 minutes on V1. Now let's do hopefully V2 a little bit faster, okay? So I'm going to erase all of these things because they were all about what was happening when we were looking for the voltage V1. So now we're looking at V2. So if I'm not mistaken, Brock chose to put the positive polarity terminal of the voltage V2 at the undotted terminal, right? So just to be clear here, I think I accidentally erased one of the things, but anyway, sorry about that. So our positive polarity is at the not dot, okay? So we're going to do our self-inductance term first, okay? So our current I1, as it flows around its clockwise path, flows into the dotted terminal of coil 2. So what should the sign be for our self-induced term for the voltage V2? Negative, because the voltage positive polarity terminal is at the not dot and the current is flowing into the dot. Absolutely right, negative. So this is going to look like negative J4 ohms times I1. Now we need to figure out there is mutual inductance between coil 2 and coil 1. So we're going to sort that one out, okay? So the positive polarity terminal is at the not dot. The current I1 is flowing into the undotted terminal of coil 1. So just to be clear here, this is the one that we're looking at. So since the positive polarity terminal is at the undotted terminal and the current is flowing into the undotted terminal, this should be a positive sign. Our mutual inductance term is J1 ohms and a current I1 is flowing into coil 1. There is no mutual inductance between coil 2 and coil 3, so we won't have a second mutual inductance term. So before we move on to voltage V3, does anybody have any questions about where these signs came from? All right, so now we're going to do the voltage V3, and I'm going to introduce how I actually like to do this, okay? So we're looking at the voltage V3. Erasing all of this kind of stuff, okay? So we can see very easily that the voltage, positive polarity terminal of the voltage is at the dotted terminal, okay? So what I'm going to ask you guys now, and this is how I do these, is so if we have the voltage at the positive polarity terminal, what is the current flowing into the dotted terminal? Negative I2. So that means we'll just have negative J6 ohms times I2. Now we have to deal with the mutual inductance between coil 3 and coil 1, right? So what is the current that's flowing into the dotted terminal of the J3 ohm impedance? Negative I1. So we will have negative J2 ohms times I1. That's effectively my shortcut for doing these quicker and not having to remember anything. Effectively, if I put the positive polarity terminal on the dot, then I want to know what current is flowing into the dots. And if I put the positive polarity terminal on the undotted, then I want to know what current is flowing into the undotted, and whatever signs I get are the correct ones. So we have these voltages V1, V2, and V3. Now we can actually do the circuit analysis. This is where it's effectively just going to look exactly like mesh, right? So all we would have is KVL around mesh 1. So first thing I see is the negative polarity terminal of my voltage source. So I'm going to have -10 angle 0 degrees volts. The next thing I see is my 4 ohm resistor. So I'm going to have 4 ohms times I1. The next thing I see is the negative polarity terminal of V1. So I'm just going to put minus V1. The next thing I see is the negative polarity terminal of V2. So I'm going to put minus V2 is equal to 0. Now I'm going to do KVL around mesh 2. So starting from the bottom left-hand corner, the first thing I see is the negative polarity terminal of the voltage V3. So I'm going to have negative V3. Then I see the 2 ohm resistor. So that's just going to be plus 2 ohms times I2. Then I see the negative J2 ohm capacitance. And the current of I2 is flowing through that. Set it equal to 0 and solve this system of equations, which is what MathCAD's all about. So once you sort out what the voltages across your coils are, this is very easy because you're just adding those voltages into your KVL equation. KVL is nothing more than just adding voltage drops together. Trylan, what's up?
Why did we derive everything? But like, we're not using any of the equations that can be found.
So we are using them. You would substitute V1 in for where you have V1 in your mesh equation. You would substitute V2 in for where you have V2 in your mesh equation. You would substitute V3 in for where you have V3 in your mesh equation. So realistically, we could do algebraic substitution here and put all those in, and we would just have a 2 equation, 2 unknown system. However, that's just algebra, boring shit. And if we're going to be using a computer to solve these things, because it's a system of complex numbers anyway, I would argue putting it in as a 5x5 equation and not doing any substitutions is just as good as doing all the substitutions and then putting it in as a 2 equation, 2 unknown system. So we have to know what those voltages V1, V2, and V3 are in terms of our impedances and our mesh currents in order to put them into our mesh equations and solve the system as a whole.
I guess, you know, you have J on I, which is something that we got to in what we just did with all of this. But I don't know. I guess maybe the fact that we went back to mesh was obfuscated from everything that we did just going
So
through that, but we don't have to go into it further.
So
yeah.
this J omega L bit right here, that just represents the impedance
Yeah.
of coil 2.
What we just.
Yep. And this J omega M is the impedance of the mutual inductance between coil 1 and coil 2. So it's the same thing. I'm just, because I didn't give you a circuit in the time domain, we got to skip the step of figuring out what the impedances are. Because we, in my opinion, did that enough when we were looking at single phase circuits. So at this point, we've got everything set up. I'll leave it to you guys to throw this stuff into MathCAD. I would rather set up another problem because that's the hard part. Putting shit in MathCAD shouldn't be hard for you guys at this point. Yes. Setting up the equations. Just like when I asked you to do nodal and mesh on exam 1, I was grading your ability on setting up the equations. The exact same thing here. Now, for particular configurations, we are going to learn some tricks and stuff like that, like using the concept of input impedance and all that kind of jazz to sort things out and not have to always use a computer for these. So exam 3 is not by any stretch of the imagination just writing out the equations and calling it a day. We are going to do other stuff that you will be able to directly calculate and all that kind of jazz. But for right now, this is what we're doing. Yep. So let's look at problem 2. So 30 angle 0 volts. Four ohm resistor. Here's our first coil. It has an impedance of J6 ohms. Dotted terminal is on the left. This one, I explicitly give you a voltage polarity. So we're going to call this Vx. I probably should have made this one the first one. I'm on problem 2. Yeah. Here's our voltage Vy across this capacitor. Here's a J4 ohm coil. Dotted terminal on the right. Eight ohm resistor. So for this one, the voltages are already defined. So I want you guys to tell me the direction of our mesh currents. So clockwise or counterclockwise for the left-hand mesh. Clockwise, okay? And then Baylor said clockwise for both. Perfectly reasonable. All right. So let's sort out the voltage Vx. Okay, so that is the voltage drop across one of our coils. Oh, and to be clear here, we have J2 ohms of mutual inductance impedance between our coil X and our coil Z, as it were. So I want you guys to tell me what you think the self-induced term for this voltage should be. So positive, why? Absolutely right. So it's going to have a positive sign. Now tell me what the term is. J6 ohms times what? I1. All right, now we have our mutual term. So what sign should our mutual term have? Negative, because the positive polarity terminal is at the dot, but the current I2 is flowing into the undotted terminal coil 2. Absolutely right, or coil Z or whatever the hell you want to call it. Okay, so negative sign. What should the value be? J2 ohms. Oh, sorry. Rock is telling me that that should be like that. Doesn't impact our sign at all that we were just dealing with. But thank you for that. So J2 ohms times I2, because the current I2 is flowing through that coil on the right-hand side. Absolutely right. All right, so now let's sort out what's going on with the correctly defined VZ, and thank you for letting me know that I had the polarity drawn backwards, Brock. All right, so what sign should my self-induced term have? Positive, because the positive polarity terminal is at the not dot and the current is flowing into the not dot. And what is the value going to be? J4 ohms times I2. All right. And now let's do the mutual term. So what sign should it have? Negative, because the positive is at the not dot and the current is flowing into the dot. So negative. What's its value? J2 ohms times I1. Absolutely right. And so now, I forgot to put the minus J10 ohms of impedance on the capacitor. So now I want you guys to tell me what my mesh equation should look like. So let's start with mesh one. Start from the bottom left-hand corner and tell me what this should be. So negative 30 angle 0 degrees. Okay. Four ohms times I1. Okay. Plus Vx. All right. So plus Vy for sure, but so Vy is a capacitor, right? So that would be negative J10. So that's the impedance. So what's the total current flowing through it? I1 minus I2. Absolutely right. And that's all equal to 0. Good deal, because you're going to need it. All right, now we're going to do our mesh 2 expression. So starting at the bottom left-hand corner of mesh 2, what are we going to have? Negative J10. I2 minus I1, absolutely correct. Ooh. So just VZ, right? We already defined it. So whenever we're dealing with the voltage drop across one of our coils, we're just going to directly substitute that in because we see the positive polarity sign first. It's just going to be plus VZ. Equal to 0, and then solve this system, and we'll be able to get everything we're interested in. So. I think it would benefit you to plug it into MathCAD for the practice and all of that kind of stuff, because you're going to be using MathCAD again for your homeworks for this material, which, by the way, has already been posted on Canvas. So anyway, so yes, to both. Yeah, got my head out of my ass real strong this morning. Let's do 1 week from today, so that would be May the 9th. Yeah. So. Nick, what's going on, bud? So we're not looking at Vy at all. I'm just saying I want the voltage drop across this impedance while I'm following mesh 2 around. Yeah. Yep. All right. So this system of equations is set up. Throw it into MathCAD. You should get the results I got. Because I asked you to solve for it? Yeah. That's one of the, I asked you to solve for Vx, Vy, and Vz. So if I didn't ask you to solve for it, I wouldn't have put a Vy in it. Now we got problem 3. So, I mean, everything is set up, so that's just MathCAD time. You can do that on your own. Yeah, we did. It's the voltage drop across that capacitor, positive polarity on top. So, I think I understand what you're saying. So VY would literally just be negative J 10 ohms times I1 minus I2. All right. Last one, and this guy's gross looking. Oh, but you will be. Or, well, you won't be a fan, but you'll be at least comfortable. Yeah. For what it's worth, this problem was actually the problem that I used for the exam in this material last year, where I asked you to set it up. Yep.
Kind of one that was like 500 and I just so and or no, especially on the exam, I was like, so you really do that, you can see the boxes and you can tell where the. It's not the same one. That's the box. I think I walk in, this is a different one, we gotta make a new one. You can tell, yeah, I know, being affected by, I want the ID, you can tell that, okay, well, I'll get my eye. You can tell, okay, the only thing I check. Except for the six on, you got it, I touch it.
All right. So in this problem, the quantities that I'm asking you to find are this voltage Vx, this current Iy, and this voltage over here across this resistor Vz. We've got J 3 ohms of mutual inductance between those two coils. We've got J 4 ohms of mutual inductance between these two. And J 6 ohms of inductance between these two. All right, so we're gonna have three mesh currents. So tell me what directions. Clockwise for everything again, counterclockwise for some. What floats for both? Clockwise for everything. Why the hell not? Yeah, not particularly.
Okay.
All right, and we don't have a voltage polarity defined for the J12 ohm coil or the J8 ohm coil. So somebody tell me positive polarity at the dot or the not dot for the J12. Positive on dot for both. Sure, why the hell not? That also seems like a reasonable thing. Let's call this voltage V1, and let's call this voltage V2. All right, so let's sort out what's going on with the voltage Vx first. Okay. So let's start with the self-inductance term. Okay. So J10 ohms. So what's the total current flowing through the positive polarity terminal here? I2 minus I1, absolutely. All right, now let's do the mutual inductance with the J8 ohm coil. So negative. J6 ohms, what should my current be? I1. Absolutely right.
Fine.
So to be clear, like the way that I like to do things here, the current flowing into the undotted terminal, excuse me, so the positive polarity terminal of Vx is at the dot for the J10 ohm coil. The current flowing into the dotted polarity terminal of the J8 ohm coil is negative I1, which gives us the negative sign here and the I1 over here. Okay. All right, so we also have to deal with the mutual inductance with the J12 ohm coil. So what's that going to look like? So we've got J3. So because we defined, or because Vx was defined with a positive polarity on the dotted side, the easiest thing to do here is to figure out the total current that's flowing into the dotted polarity terminal over here, and then give ourselves a plus sign. So what current would that be that's flowing into the dotted terminal of the J12 ohm impedance? I3 minus I1. So I believe that is all correct. Carolyn, you have a confused look on your face. Can I attempt to explain things? Sure. So when I3 goes around its clockwise path, it's flowing into the dotted terminal, so it's going to get a plus sign. When I1 flows around its clockwise path, it's flowing into the undotted terminal, so it gets a minus sign. And put a minus sign in front.
Right,
Mhm.
because that means you're treating I1 equal to positive terminal. I mean, we can do that, but I'm just asking.
Yeah. Yeah. All right, so any other questions on our voltage Vx? All righty. So now let's sort out what V2 is. Okay. So just putting a little circle around this so that we can remember. The positive polarity terminal for V2 is at the undotted terminal of the coil, so that's kind of our reference thing. So what's the current flowing into the undotted terminal of the J8 ohm coil? I1. So we're just going to have J8 ohms times I1 as our self-inductance term. What is the current flowing into the undotted terminal of the J10 ohm coil? The current flowing into the undotted terminal of the J10 ohm coil. So I1 is part of what's flowing into the undotted terminal. I1 minus I2, absolutely right. So we're going to have plus J6, which is the mutual inductance between those two coils, times I1 minus I2. And now we have to sort out the mutual inductance term with the J12 ohm coil. Okay. So what is the current flowing into the undotted terminal of the J12 ohm coil? I1 minus I3. All right, and then lastly, let's sort out the voltage V1. So the positive polarity terminal of voltage V1 is at the dotted terminal of the J12 ohm coil. So what is the total current flowing into the dotted terminal of the J12 ohm coil? I3 minus I1. Absolutely. Now let's do the mutual inductance with the J10 ohm coil. So we're going to have J3. What is the total current flowing into the dotted terminal of the J10 ohm coil? I2 minus I1, absolutely right. And lastly, we have our mutual inductance with the J8 ohm coil. So that's going to look like J4. What is the total current flowing into the dotted terminal for the J8 ohm coil? Negative I1. So minus I1. And now we would just do, because this current I1 is flowing into the undotted terminal, and the positive polarity of V1 is at the dot. So negative I1 is flowing into the dotted terminal, so it's positive negative I1, or just minus I1. All right, we've only got like 2 minutes left, so I think this will be a good place to stop for this. You guys could write your mesh equations if you were so inclined, just using the good old mesh analysis techniques that we've been using for months at this point. Yes. When you say the relations, you mean this stuff? Yeah. All right. You guys have a good weekend, all this kind of stuff.